our next speaker for the day is Balaji, who will be speaking on Make Your Own Go Debugger. Balaji is the co-founder for Streak. Please welcome Balaji.
Hi everyone. Today I'll be talking about how to build your own Go debugger. A year back I was working on a project called QuickLog. It's a real-time debugging solution. That time I was curious about how debugger works. That curiosity led me to explore the internal working of debugger. I'll be sharing whatever the limited knowledge I gained during those exploration. About me, I'm Balaji. I'm the co-founder of Streak, which is funded by YC, and also an early adopter of Go language. I've been doing Go for more than 4 years, and back in that time when Kubernetes was coming, I was contributing to upstream. Then I also do Rust. Some of my projects are Inspector. It's a centralized access control solution, and also have a good experience in networking and distributed systems. Right now, I do a bit of cold reach out as well. How do you debug a program? Whenever you have a bug in your program, the typical way would be having a print statement, see whether your code is working or not. I use print statement a lot because the feedback loop is higher than using a debugger. But there are some places code is very complex. It's hard to have the entire mental model on your head. That time, I tend to use a debugger. For Go, there is a debugger name is called Delve. So that is used to debug your Go program. The one disadvantage of using debugger, according to me, is that it's really big. Putting a breakpoint over the entire flow is difficult. So what I tend to do is that I write a small unit test case and I put all this debugging breakpoint so that your feedback loop is higher than you run the entire program and debug it. But this is my opinion. There is no right way to do it. Some people like to use Vim. Some people like to use VS Code. I'm the guy who likes to use VS Code. So before we learn how debugger works, let's have a basic understanding what debugger is. So this is a simple Go program which has a for loop. And there's a variable called variable trace, which has a random integer has been assigned to it. Then I'm just printing it and sleeping it. It's just like infinite loop. So I'm just setting a breakpoint at line number 12. And VS Code has this huge integration. You don't need to use all this command line jargons. You can click, run and click. So you can clearly see that fmt.println, the program is passed there. It's supposed to print something on the console, but it didn't print because the program is passed there. So when the program is passed, you can see the entire, what is the local call variables on the left side, so that you don't need to write all this print statement. You can see everything on the left side, and you can debug easily. You don't need to println variable A. Then after you forgot, you have to it's not A, it's B. Then after you put the B and run it again. But here you can do everything. You stop it and see everything on the left side. Not just that, if you are going over the new code base, once you pass it, you can do run one by one. Or you want to go inside the call stack and go outside the call stack. This is called step in and step out. And just close it. Yeah. Let's do a small rewind. The red color point we put on the left side, That's called breakpoint. That is the place where you want to pause. Then step in is just like you want to go inside the function, and step out is like getting out of the function. And whenever it's paused, you can see the local state. It's like you can introspect the current state of the program. Cool. We got the understanding what debugger is. Let's just understand how debugger works internally. So we want to set a breakpoint that red color dot what VS Code does. So for that, what do we have? We have a source code. Then from the source code, we can derive the binary, which is go build dot. But the thing is, whatever you write in the higher abstracted language, which is Go, when you compile it, that will turn into an assembly language. We have to find, let's say that print statement which were in the sample program, that is line number 12. We want to find the line number 12 in the assembly language. How do we do that? Because like it's all like fmt println, it must be like move or some register it goes and put it on the device console. So how do we do that? We have something called DWARF. DWARF is a metadata that will be shipped along with your binary that helps you to find the mapping between your higher level language towards the assembly. For that, I'll be using a tool called objdump that help you to find the mapping of your higher assembly towards the higher level language. Right now, I pass this flag DWARF is equal to decode line and give the path of this binary. It gives you this output similar to this. I just copied the snippet of it. You can clearly see that line like sample.co line number 12 is at the virtual address 0x498233. So we exactly know where the line number 12 in the assembly of the memory region. But there are few, like this mapping, you won't find it everywhere. That is because inline function. Let's say you have a small function which has like add, which passes parameter a comma b integer, it returns a plus b. Since it's a small function, what compiler does it that it won't do so functions it does the stack jump and goes up and down so that like you can reduce the memory binary size. That's why we use function. So when it comes to a small function, compilers tend to like put the assembly in the same function so that you don't need to like jump here and there. To avoid those inlining, you can do this command directory go : no inline. And also like when you're building your application, you can pass this DC flag and you can build the application so that like none of the DWARF symbol get missed out. Then you can see this mappings clearly. So we know that like where is line number 12 in the assembly language, but still we don't know how to pass the program. All we know is that where that is in assembly, but we don't know how to pass the program. The trick to pass the program is to rewrite that assembly instruction with 0xcc, which is integer 3. Once you rewrite it, then your program will get passed at wherever you want to get passed. How do we like rewrite it? Should we like rewrite the binary, go to that place and like rewrite it? Actually, no. So what do we do then? Unix has this list of system call called ptrace that allows you to manipulate the running process memory in real time. This is what Delve uses internally. This is what like most of the debuggers also uses. So right now we know like we converted like where to find that line number 12 in assembly and how to pass the program. That is by introducing the trap code. let's see like how do we use this ptrace in Go and programmatically manipulate and set the breakpoint. So let's start the program. This is simple Go, like I'm running a child process from the parent process. I have given this binary path and doing like process start from my main process. It spawns a child process. Then setting this breakpoint. These are the few calls that we debuggers essentially use. One is ptrace.poke data. Using ptrace.poke data, you can rewrite the memory region with whatever you want to rewrite as. So you just have to mention this address, the mapping, you saw the virtual region address, then you put the 0xcc, then it rewrites. But we have used another syscall called ptrace peak data. That is used to read the data from the region. I'll tell you why we have to memorize the existing instruction in the upcoming slide. Right now, you can think it like we are memorizing what is the existing instruction at the line number 12. And then after we rewriting the instruction at the line number 12 with this trap signal, trap code called 0xcc. Then we continue the program. To run the process, we use ptrace continue, cont. Then we wait, that unix.wait, it's a blocking call. That will be blocked till that line number 12 has been hit. Then the signal will be given to this parent process. Till then, this process will be like blocked. Then my dumb way of debugging is to add the println statement, then like breakpoint hit. This is how like, okay, breakpoint is working. Then how do we resume the program? When the breakpoint is hit, we have to resume the program, right? Because like the code we want to execute is line number 12, but line number 12 we have rewritten something else. How do we resume the program? Is to revert back. This is why I told in the beginning why we have to memorize the existing assembly code at the line number 12, so that we can revert it back and let the flow execution as it is. But there is one more problem on top of it. Because line number 12 is already executed, that's why we got this trap signal, right? So like the next if you do ptrace continue, line number 12 won't get executed. Instead of line number 13 will get executed. How do we like make to execute the program line number 12 again? This is where register comes. Back in university or college, we might have like studied a program counter, and I don't know, like we had something called microprocessor. They were like teaching all this register. So what program counter does is that it tells what is the next instruction we want to execute. So we want to manipulate the register right now. So we have to tell the register that like we have to like change the program counter to the address, which is line number 12 address, so that the line number 12 get executed again. So, but you can see program counter, it's called RIP. It's not rest in peace. It's called instruction pointer. That's like the name goes, program counter and instruction pointer. So we set the registers. Okay, we have set the registers. Let's run ptrace continue. What happens? It keeps running. But does it breaks again? No, because we reverted it back. How do we like reset the, like we have to like after line number 12 execution, we have to put the 0xcc back, so that whenever that line number 12 executes again, it'll get stopped over there. So for that, after we set our registers, there is one syscall called ptrace single step. What it does is that it just execute one instruction. It doesn't, the CPU doesn't make it to entire flow. It's just like after 13, 14, 16. It is like after 12, you just execute only 13. Once you execute only 13, then we put the breakpoint again. So that whenever 11, 12 executes, it stops there, pauses there. So idea would be like you set the breakpoint, then you got the signal, you revert the original address and like set the register to execute just the breakpoint location again and set the breakpoint back. This is the simple logic loop that keep happening in the debugger, and that is your simple debugger state machine. I guess yeah, right now we learned how breakpoint works. From here, you guys can learn how do we using DWARF symbols where the variables are. If it's an integer, you can go to that region and read 4 bytes from now, then get all the stack. And this is how del works, and show it on a UI on the left bar. Thank you guys.